Yeah, well, my thanks to the organizers for a very kind invitation to come speak here. And I hope this is a very timely talk. I want to ask exactly what Norbert just asked. Have we seen a demonstration of experimental quantum advantage? And one thing I would sort of invite questions at any point, so please don't sort of leave them to the end. Happy to take them at any time. Okay, so the starting point for this talk, which I think will surprise precisely no one at this point, is that we've now seen the first quantum advantage claims, right? We've seen them actually many times. First, very notably by Google in late 2019, who implemented the so-called random quantum circuit sampling proposal with 53 superconducting qubits. They're still working on this. So even as late as a bit earlier this year, they had a sort of bigger random circuit sampling experiment. It's a little bit less noisy. So they're still sort of thinking about this quite a bit. And then sort of in parallel, we've seen the so-called Gaussian boson sampling proposal for quantum advantage in a linear optical architecture. And we've seen several implementations now by a group at USTC in China and Xanadu, a Canadian startup company. And they've been like producing better and better, sort of bigger, less noisy experiments like every single year since like 2021. But in this talk, I kind of wanted to take a step back and discuss the sort of latest rigorous or complexity theoretic arguments to understand these random quantum circuit experiments. And in fact, both of these are just different special cases of random quantum circuits. So while experimentally they're very different, theoretically they have a lot of similarities. Okay, but first things first, what's the ideal goal of quantum advantage? What are we trying to achieve? I think this is already somewhat controversial, actually.
It's a recurring theme we already had yesterday.
Yeah. Oh, really? Okay, I see. You guys already know. This is pretty controversial, so let me add to the controversy and tell you my opinion. Okay, so this is what I would like to see. I think we should find a problem with three properties. First, that it can be solved using a near-term quantum experiment. So, for example, we don't want to require fault tolerance or too much error mitigation. Right? That's great stuff, but of course it's quite futuristic still. Okay, now, we want this problem to be classically hard to solve. And here, I think we need to hold ourselves to a really high standard. In my opinion, it doesn't suffice to say that the best classical algorithm that we currently know of, invariably some tensor network algorithm, right? Running on Google's fastest classical supercomputer takes a long time to simulate this, to solve this problem. I think that's necessary, that such an algorithm doesn't solve the problem very quickly, but it's not sufficient. I think what we want to show is going to be very rigorous here and prove that this problem cannot be solved by any classical algorithm that will ever exist that makes a polynomial amount of running time, okay? So this requires complexity theory, right? There's no way to get around this. Complexity theory is our language for expressing these sort of algorithm-independent hardness results, okay? But then finally, we want that the solution to the problem can be efficiently verified with a classical computer with minimal trust in the experiment. And I think this minimal trust bit is really important. And it's not, contrary to popular belief, it's not because we don't trust our experimental colleagues, right? That's not the point. The point of this is I want to think of quantum advantage as a test of quantum mechanics in a new sort of high complexity regime that we haven't seen before. And if we're thinking about that, if we're thinking about it like that, that quantum advantage is a test of quantum mechanics itself, then we have to be really careful that we don't make some very strong assumption, say about the noise model of the system, to get quantum advantage. From my perspective, if we make too strong of an assumption, it's very clearly like assuming something about quantum mechanics to test quantum mechanics, which becomes circular. Okay? So we have to be extremely careful what sorts of assumptions we make. Particularly, I think this will be relevant when we talk about the noise toward the end of the talk, okay? It's very, very important that we don't make too strong of an assumption about the noise to get quantum advantage. Okay, so far I've said nothing particularly formal, but this is already, I think, somewhat controversial, so I want to make sure that there's no questions. Does anyone have any questions about this? Yeah. Aha. Yes, not by coincidence. Let me be very clear. for political reasons, and because I find it, I'm not a huge fan of the term myself, because I think a lot of people are insulted, I do not call this quantum supremacy. However, right, I'm talking about exactly the same thing as quantum supremacy.
But doesn't quantum advantage already have a different meaning?
Quantum advantage means to, different people whatever they want to mean. This is what we're going to talk about. Okay. Other questions? Okay. Now, I think by these standards, it's very clear that we haven't hit quantum advantage, but we've made a lot of progress. So what's the status quo? Let me tell you in one slide. Current quantum advantage experiments, in fact, all of them, every single claim so far, solve a sampling problem in which the goal, the problem that they're solving, is to sample from some complicated distribution that's implicitly specified by a quantum circuit and a measurement. Okay? That's the problem that they're solving. Now, we'll discuss the latest evidence that these problems cannot be solved in polynomial time. These are very rigorous complexity theoretic mathematical arguments. But I want to be really clear here, because I think this is often misunderstood. What these arguments are, the goal of these arguments, these complexity theoretic hardness arguments, are always to show that there should not exist a classical algorithm that runs in a polynomial amount of time as the system size scales. Right? So fundamentally, these are asymptotic arguments about the hardness of the problem as the system size is getting larger. Okay? And this is what complexity does. We don't have a good complexity theory for non-scaling systems, for fixed system sizes. And so this already gives a profound disconnect, right, between the theory on the one hand and the experiments. And this is quite severe. Okay? It's not just that experiments are implemented at a fixed system size, n equal 53, and not n scaling. It's more severe than that. It's that there's fundamental reasons why current quantum advantage experiments are not scalable. In fact, there are two of them. One, the verification, the way that we check that these experiments have been implemented properly, is fundamentally inefficient. In fact, what we really do to verify these sampling experiments in all cases is run some simulation. We compute some output probability, some measurement outcome probability of the random quantum circuit, or whatever we're doing, right? It's fundamentally the same task that we're proving is hard in the first place, right? So there's sort of a circularity here, and we don't know how to address it. But what it means is, at least in the current era, if we keep making our system size larger and larger, eventually we will not know how to check that it's solving the right problem. Okay. Second, and I think this is more important from my perspective, we think a lot about this. Uncorrected noise, which is, I think, the sort of defining characteristic of the near-term quantum era, causes the quantum signal, let's say measured by the fidelity of the system, to rapidly decay. Right? So it's very clear that if we take our 53-qubit random circuit sampling experiment, we make it larger and larger, and we don't proportionally drop our noise rates, right? Eventually we're going to get garbage. We're going to get something that we have no means of measuring. Right? It's absolutely no, and theoretically speaking, the signal is just too small. Okay? So it's true that we need these complexity theoretic arguments. We'll talk about them a lot. I like them a lot. We think about them constantly. But I want to be really clear that they're not sort of the end of the story. Right? In particular, they're operating in a regime that fundamentally is not the regime that's operated by in these experiments. Instead, I would say the game these experiments are playing is a little bit different. Right? So what I'll say is these two issues force current quantum advantage candidates to find what I call Goldilocks parameter regime. So if you know the story, you know exactly what I mean. If you don't know the story, you have a little girl, she goes into the woods, she meets her friends, the three bears. One is a big bear, one is a medium bear, and one is a small bear. And the moral of this story somehow is that the opinions of the medium-sized bear are always correct. Okay? That's the goal. And this is exactly what we're looking at in quantum advantage. When we think about a system size, we want a system size that's clearly not too small. Right? If it's too small, it becomes easy to simulate, and sort of by definition. But if it's too big, we're not going to be able to verify the experiment. And the experiment will become too noisy, and we're not going to be able to measure any signal in that experiment. right? So rather than looking for sort of larger and larger and larger system sizes, which is the regime that complexity talks about, complexity theory is always about scaling, right? We're trying to find a Goldilocks parameter regime. Now, there's some optimism that the most recent experiments have been implemented in such a Goldilocks regime, but I want to be really clear about this, right? It's a very precarious situation, and it always will be a precarious situation because fundamentally, we don't have rigorous evidence that, we've reached this sort of Goldilocks regime. It doesn't even make sense because complexity doesn't work in this, all of our rigorous arguments are complexity theoretic, and they're talking about scaling, not the Goldilocks regime. But nonetheless, this optimism exists. But of course, in a few days, it could be that someone discovers a better algorithm, right? Or their classical computer gets faster. And we've seen this now several times. There've been several iterations of this, of sort of new, different claims, then a better algorithm, and so on. Yeah.
Well, isn't this Goldilocks regime exactly the one where mass is the weakest? We're very good in large numbers and small systems.
Yeah.
And are you not asking us to do this thing we really don't know what to do?
Exactly. No, that's exactly, to be clear, it's exactly the issue, and that's the challenge. It's a very, very challenging thing.
I mean, there's this
Totally.
where we're just completely stupid.
Absolutely, absolutely. And we can keep talking about the complexity, and I think that's important, but we also have to keep in mind that the complexity is just not talking about the regime that these experiments are operating in. And on the other hand, though, I think there's a really interesting question here. And in some sense, the interesting thing about this question is that it's not trivially false. But it's not, which is, is this situation, this sort of Goldilocks situation, is that inevitable in the near-term era, right? In other words, does there exist any asymptotic computational advantage for any near-term experiment? And here I mean without correcting your noise, right? And again, your bias here, your a priori, the answer should be no, right? If you're not correcting your noise and you're making your system larger and larger and larger, sort of intuitive that you're not going to get any reasonable signal. But what's sort of surprising, and we'll talk about this again at the end of the talk, is that there are several scenarios in which I can't prove that that there's an algorithm to simulate these noisy quantum systems in the asymptotic limit. Okay. So again, we'll come to that. Can I take questions about this? Again, be surprised how controversial these things are actually. A lot of the debates of quantum supremacy, quantum advantage, and what has been done, what hasn't been done, would be resolved if we could all agree about this slide, I think. Yeah.
You have asymptotic and near-term in the same sentence.
Sorry, asymptotic and near-term in the same sentence. Yes, exactly. Exactly. What I'm asking is, can you take the current experiment, like say the 53-qubit random circuit experiment for Google, it doesn't matter. And is there a sense in which you could make that a 54-qubit experiment, a 55-qubit experiment, and so on? Still don't correct your noise, because that's the near term. That's what I mean by near term in all cases. And will you, is there actually a rigorous sense in which we can say you get a quantum advantage with that or not? Right? That's a really, it's really unclear. It's really, really unclear. We'll make this more rigorous in a moment, though, I promise. Any other questions? Yeah?
Do you consider error mitigation in the near term? Or what do you mean by near term here?
Right, good, yeah. No, in this discussion, in all of this talk, I'm not considering error mitigation. And I'm just defining that to be near term. Now, of course, one way to get out of a lot of the sticky situations I'll discuss when it comes to noise, the end, will be to use some sort of error mitigation, maybe not full-blown fault tolerance or error correction. But just to be clear, I'm not discussing any of those things in this particular talk. It's not because I don't like it, it's just that would change the theory quite a bit. Okay? That's a good question, though. Yeah?
Why do you insist on scaling the number of qubits with the noise fixed instead of like
I didn't. No, I didn't. I didn't say that. Did I say the noise was fixed? No, that's one scenario we can consider. We can also consider a scenario in which the noise is decaying, right? We'll talk about both of those things. Yeah. But just to be clear though, computer scientists like this fixed noise model better. And the reason is because if we're really honest with ourselves, when we're thinking about what these asymptotic arguments mean, this 1/n noise rate doesn't make that much sense, because we're thinking about n is ginormous, right? I think it's very reasonable that when you have system sizes that are like 50, 60, 100 qubits, reasonably small, you can continually decrease your noise. But eventually, the whole point of fault tolerance, the whole point of the threshold theorem is that we don't have to play that game, right? That's the whole point. So we want to be careful that we don't want to talk about that too much, although I think it's an interesting regime. Other questions? These are good. I'm always shocked that everyone isn't raising their hand at this point. Yes?
So I think many problems, you don't see hardness results until you're like sufficiently large system size.
Yeah.
So to fall into this Goldilocks rules and your previous three criteria, this limits us to a very specific number of problems.
Absolutely. 100%. Totally. Right. And it's not clear that this Goldilocks exists for any problem. Not at all. Right? It could be that we just missed this Goldilocks era completely because the best algorithms can take advantage of noise. Maybe they're not efficient asymptotically, but they're doing so well that you have to have a very large system size before the algorithms really start to struggle, the classical simulation algorithms. And it's too hard to implement those sizes with the noises that we'll need. It's a possibility, right? It's not a possibility that I think is ridiculous, by the way. Yeah. The solution here is very clear. It's fault tolerance and error correction. But I'm defining near term in a way so that you can't use that. Okay, let me keep going. So, what's random circuit sampling? What do we mean? What we want to do is generate a quantum circuit C on n qubits on a 2D lattice with D, which is some parameter, which could scale with n, layers of random nearest neighbor gates. Right? So each layer might look something like this. The circles here are qubits. The edges are random nearest neighbor gates. Then this could be the first layer. The second layer could look different. For example, we might imagine connecting the horizontal neighbors with a gate rather than the vertical neighbors, right? But the point is, in any case, we start in the all zeros input state for each of our n qubits. We apply D different layers of a circuit like this. We measure all n qubits in our computational basis. We then think about sampling from a distribution, which I'll call D sub C, which is a distribution over n-bit strings. That is the problem that we are solving always when we think about random circuit sampling. Okay. Now, it's been implemented several times, first by Google in 2019 with n equal 53, D equals 20, and most recently in an experiment with it's a little bit bigger, 70 qubits. The depth is somewhat similar, 24. But the really impressive thing about this experiment, which is not on this, about this latest experiment, which is not on the screen, is in fact the sort of overall fidelity, the 70 qubit fidelity of this experiment and the 53 qubit experiment were sort of within the same general order of magnitude, which means that, of course, this, the 2 qubit gate error rates are going down dramatically. Okay? So in fact, this is not only a bigger experiment, it's also a much less noisy experiment. Okay? Okay, but that's fine, that's the experiment, and that's very important. But our question is, why should random circuit sampling be classically hard? And this is not obvious at all, not even close. Okay, why should implementing randomly chosen quantum circuit, which is like choosing your code randomly, and measuring, getting a sample, why should that have any hard signal at all? Even before noise, not obvious at all. Right, so the first goal is that we're going to have today is to try to prove the impossibility of an efficient classical sampler algorithm that essentially simulates an idealized version of this random circuit sampling problem. Namely, it should take as input the classical description of a random circuit C, should output a sample from D sub C with high probability over the choice of C, and we're trying to prove that such an algorithm does not exist. Okay, and I want to be really clear here, because this is messed up in the literature all the time. When we talk about these complexity arguments, we're not directly modeling physical noise. The right way to think about these complexity arguments that I'll describe is just, even without noise, is there a hard signal in a random quantum circuit? Okay? I want to be really clear about this because people have tried to introduce noise in various ways. Generally speaking, complexity does not cooperate well with uncorrected noise. Okay? For exactly the reason we discussed, because complexity theory is talking about asymptotics. All right, so we're going to talk about noise, it's very important, but we're going to first talk about the case with no noise and try to at least pin down that there's a signal, and maybe somewhat surprisingly, we'll see that there's a lot of open questions even there. We won't fully be able to finish this discussion, okay, to prove that there's no algorithm that does this, a noiseless simulation of the random circuit, okay? All right, cool. So How do we start the proof? Well, it turns out computer scientists are not so good at talking about the hardness of sampling problems directly. That's not generally what we talk about. So the first step in every single quantum advantage analysis is the same, which is to invoke a well-known reduction due to Stockmeyer in the 80s, which says if the goal is to prove hardness of sampling, then it suffices to prove that another problem is hard. And that problem is giving a certain additive estimate to the output probability of most random quantum circuits, and the goal is to show that it's sharp P hard. Now, if you know what sharp P is, that's great, you understand this. If you don't, it means very hard, okay? No, let's formalize this a little bit. So the goal is to prove the hardness of estimating what I'm calling the output probability. That's this P0 to the n quantity. It's just exactly what you think it is. It's the probability you start in all zeros, you apply your circuit, and you measure and you get back all zeros. That's the output probability. All right, within additive error, 2 to the minus n. This 2 to the minus n is super important. It's 1 over the Hilbert space dimension. It's not an arbitrary inverse exponential quantity. It's 1 over the Hilbert space dimension, super important. With probability 2/3 over the circuit. Okay, so in other words, how hard is it to compute a good additive estimate to most output probability, the output probability of most random circuits with probability, where most here means probability 2/3. That's the question. Now we think about the Stockmeyer argument as working in the context of a proof by contradiction. So we say, let's say for contradiction there does exist a classical sampling algorithm. That's what we want to show is not the case, but let's say that it does for contradiction. Well then what the Stockmeyer reduction tells us is there's also another algorithm. That algorithm is not efficient, but that's not super important for us today. What it does is it gives an estimate to the output probability of most random quantum circuits. And again, estimate here means 2 to the minus n additive error. N is the number of qubits, right? Now, the goal is to show that in fact this algorithm for this bubble here is too good to be true, shouldn't be able to exist, right? Because we're trying to prove that this is a hard problem, so hard that we cannot solve it, even with this NP oracle. Right? And therefore, by the Stockmeyer reduction, that this classical sampling algorithm cannot exist. Okay? So the goal of our discussion here is going to be to prove this statement, to prove that this estimating output probability bubble is a hard problem, right? But it's in the context of a proof by contradiction to show that there exists no classical sampling algorithm.
So is it the same kind of argument as approximate counting, or is it a different stuff? It
is approximate counting, totally.
Just have to think sharply about it and understand it's the same.
What, sorry?
It's not completely obvious to me it's the same as approximate counting. It feels similar.
It's only approximate counting. It's the only thing that you do. Yeah. Mm-hmm. Okay, so this will be the goal. Now, let me tell you my inspiration. So all of the hardness results from here will be inspired by this result in complexity theory in the early 90s due to Dick Lipton. It's a very beautiful argument, one of my favorite arguments in complexity theory, so I insist on telling it to everyone I see. And it shows the average case hardness of computing the permanent. That is, that the permanent is hard even for a random matrix. Okay? Computing the permanent for most random matrices is as hard as computing the permanent of an arbitrary matrix. And the starting point is that, Lipton is following up on a very famous result by Les Valiant in the late 70s, who had shown that computing the permanent of an n by n matrix is hard in the worst case. Right? So that means that we don't expect an algorithm, efficient quantum or classical algorithm, to compute the permanent of any matrix, of any arbitrary matrix. Okay? And it's a very surprising, one of the most famous results in all of complexity theory, particularly because the permanent looks superficially similar to the determinant, and yet the determinant is easy. You solve it all day, like Gaussian elimination. The permanent is not only NP hard, but sharp P hard. So much, much harder. Understanding why there's this giant gap, presumably in the complexity between the permanent and the determinant, one of the most famous sort of unresolved questions in complexity theory. Okay? All right, but fine. Lipton is interested in more, though. He wants to show that the permanent is not only hard in the worst case, that means for any arbitrary matrix, but for a randomly chosen matrix with high probability. And to do this, he's going to make use of a very simple algebraic property of the permanent, which is that the permanent is a degree n polynomial in the n squared variables. And the n squared variables here are the n by n matrix entries, right? And that's, of course, not at all hard to see from the expression of the permanent itself, okay? All right, so now what's the setting? Well, the goal is to compute the permanent of a worst case matrix. That's a matrix that you give me. You tell me, Bill, you must compute the permanent of this matrix X. It's whatever matrix you like. That's what I mean by worst case matrix. Oh, and we're going to make its entries in a sufficiently large finite field. And that's important for this argument. So FP. OK. But I only have at my disposal by assumption, OK, a faulty algorithm or an average case algorithm O that works to correctly compute the permanent of most matrices. Right? In other words, this is what O does. O is given a randomly chosen matrix, and what we're guaranteed is that O correctly computes the permanent of that matrix with sufficiently high probability over the matrices, right? Like 1 minus 1 over some polynomial. Okay? But the point of it is that it's a faulty algorithm with, for a 1 over polynomial fraction of these matrices, Y, O might output complete nonsense. And from the end user of O, from their perspective, we have no idea when it gets it right and when it gets it wrong, just that it gets it right most of the time. Yet, what Lipton shows, and I think a really nice argument, is that, really simple, beautiful argument, is that in fact you can use such a faulty algorithm O to correctly compute the permanent of your favorite matrix. Okay? That's what he shows. Therefore, the permanent is as hard on average as it is in the worst case, which is sharp P hard. Okay, so how does he do this? It's a very simple polynomial extrapolation argument. So what he does is he chooses n plus 1 fixed non-zero points in our field. So we'll call them T1, T2 through Tn plus 1. So our points in Fp, and then a uniformly random matrix R. Okay? Now, he's going to consider the line A of t is equal to x. That's the worst case matrix. It's the matrix we want to know the permanent of, plus t times R. Okay? 2 observations about this line, and once we have the observations, we'll essentially be done with the proof. Okay, first, I call this the scrambling property, which is that for each I individually, A of t sub I is a uniformly random matrix over our finite field. That's not hard to see, right? Because what did we do? We just took x, that's our fixed matrix, we shifted it, right? We shifted it by something uniformly random, so the output is uniformly random. That's all this is saying, okay? Observation 2, even simpler, is that there's a univariate polynomial hiding here, right? Which is that the permanent of A of t, okay, is a degree n polynomial, but now in a single variable, t. That's, again, inherited from the algebraic property of the permanent itself, right? But now I've introduced the parameter t. Now it's a single variate polynomial. All right, so this sort of spells out how the proof should work. Let me tell you what we're going to do. Let's assume in the beginning that the box is not faulty. Right? So it just gives us the correct permanent. Of course, we have to add our faults. That's the whole point. But let's assume that O of A of t is equal to permanent of A of t. Okay, always. Well, then it's sort of clear what we should do. Right? We evaluate O at A of t1. We evaluate O at A of t2, all the way through n plus 1. Now we've specified a degree n single variate polynomial at n plus 1 points. Right? And so we can take these points uniquely define the polynomial, because it's a degree n polynomial, right, the n plus 1 points. And we can use grade school polynomial extrapolation, right, to reconstruct from these points the permanent of A of t, that polynomial. Okay? Once we do that, it's trivial to get back the permanent of x by evaluating t at 0. Right? Because when t is equal to 0, A of 0 is equal to x, clearly. Okay, now, I'm going to claim this works even if the box is faulty. And to see this, we can do the following. So I didn't tell you what this polynomial was, but let's say it's like 1 over 100 times n plus 1, something like this. Well, then what you can say is that by a union bound, okay, with very high probability, 99%, whatever it is, whatever constant I said, all of these n plus 1 points are correct. Right? Now, they're correlated, but remember, union bound does not care about the correlations. Okay? And so, with probability 99%, all of these points are correct. Once they're completely correct, I have n plus 1 points, the rest of the argument works. Okay? Now, so that's why this proof works. One thing I'll say, though, is that I only gave the simplest case when this is a very small polynomial. In fact, a major sort of research agenda and complexity over the last, 30 years or something like this has been to make this sort of the success probability smaller and smaller and smaller and smaller using correspondingly more sophisticated techniques. So in fact, there are arguments that say even if this is like 1 over poly, not 1 minus 1 over poly, right? You can still use more sophisticated techniques to make this sort of argument work. We're not going to go into those techniques. Those are a lot harder. But the point is this is a polynomial extrapolation argument. Any questions? Yes? Why a finite field? Yes. Yeah, good. Yeah. Hold on. We're gonna come there because of course when we're talking about random circuits, we're not going to be talking about finite fields. So we'll have to adapt that. We'll see that we're sort of.
But why did you use it up to now?
Well, one thing we used is if you have x plus t times r, that's uniformly random.
Oh, I see.
That's a property of a finite field. We're gonna have to be like, we're gonna get over that, but it's gonna take a lot of work, okay, in the quantum circuit case, precisely because we're not talking about finite fields.
It seems that P has to go with
Precisely. Yes, please.
Are you sure there's no connection to error mitigation in this page?
Hold on. This is an error mitigation. This is clearly an error mitigation. You caught me. This is an error mitigation result, clearly, right? And in fact, the way we extend on this, which I'll explain in a moment, it totally uses error correction methods. I simply meant, though, and I think you knew this, that in the experiment, we're not error correction. This is all about the analysis. Yeah, but a good question. Yes.
So just to make the connection with the determinant, because for the similar, you just have the -1 to a given power.
Yeah.
If you were to try it, clearly you cannot extend this to the determinant because that doesn't happen there. There's a part where it fails. Is it like the poly?
Good. That's a great question. I give that to often my undergrads when I talk about complexity class. It's very important. No, it doesn't fail there. In fact, the determinant is also a polynomial in exactly the same argument. But can someone help me out? What does fail? There is a step here that fails. The worst case, exactly. The worst case for determinant is no longer sharp P hard. So in fact, this does absolutely prove that the determinant is as hard on average as it is in the worst case. It's just that the determinant is easy in the worst case, so it's not a very interesting statement. Okay, excellent. Let's keep going. So what do? So what we're trying to do is adapt this from the permanent of a random matrix to the output probability of a random circuit. And the first thing we notice is that there's an algebraic property here too. Much like the permanent, the output probability of a random quantum circuit has a polynomial structure. How do you see this? Let's consider the circuit C and let's break it apart into its 2-qubit gates. So Cm times Cm minus 1 and so on. These are 2-qubit gates, okay? Now, the polynomial structure comes from the path integral, which says we can write the output amplitude, that's this quantity here, before we square, as a giant sum. It's a sum over an exponential number of paths, okay? But the point is the value of each term individually is really easy. It's really easy to understand. It's just the product of m gate entries. That's all it is, okay? So it's a giant sum, but each term is quite simple. And, it's not only simple, it's a polynomial of degree m in the gate entries of the circuit. Well, that's easy to see. Okay. All right, so then we square things, so the probability is going to be, by the Born rule, is of degree 2m. Okay. So now what does Lipton do? He takes a fixed circuit, a fixed matrix in his case. He does something to scramble it because he wants to make it more random. How do we scramble a random circuit? Here's one way. It won't quite work, but it will fail instructively. What we can do is we can fix m 2-qubit gates that are Haar random, so H1, H2, and so on. These are just chosen Haar randomly. And then we can consider, scrambling the circuit in the following way. The ith gate of the scrambled circuit, which I'll call Ci prime, is Ci times Hi, right? So that's Ci, it's a fixed gate of our worst case circuit, times Hi, that's Haar random. So now by the invariance property of Haar random, the definition of Haar random, this is Haar random, totally scrambled. But now we need to do more. So what we do is we multiply by e to the minus I little hi theta, where we think of little hi as the log of big hi. Okay? And the point is this has a Lipton-like property, right? If theta is really tiny, then this actually scrambles really well. It's not totally scrambled, but it scrambles really well, because each gate then is close to Haar random. If theta is tiny, right, we're doing almost nothing here. That's the intuition. Yeah? But if theta is 1, so if it's not small, that's what I mean, then in fact, we cancel the HI. We get HI times HI inverse, and that gives us back C, our worst case circuit exactly. This is very similar to the structure of Lipton's proof, right? Okay, so then what's the strategy? This is very much like Lipton. We'll take several non-zero but small angles theta, right? For each of these angles, we have a corresponding random but correlated circuit. We'll call that C prime of theta 1, C prime of theta 2, and so on, okay? Then we use our faulty algorithm to compute the output probabilities of each of these circuits, and then apply a polynomial extrapolation argument to reconstruct some polynomial in a single variable theta. Once we do that, it's trivial to get back the output probability of our worst case circuit by evaluating this polynomial at 1, because when we have 1, when theta is equal to 1, the corresponding circuit is not scrambled at all. Okay. This almost works, but it fails for a really silly reason that caused us a lot of heartache a few years back, which is that, it's very simple, e to the minus I little hi theta is not a fixed degree polynomial in theta, right? If it was, we'd be happy, but it's not. So what do we do? What would a physicist do at this point? This is our first
Try to fit with an exponential.
truncate the Taylor series. Isn't that what people would do? I think that's the first thing a physicist would do. Yeah, yeah, that's the second thing a physicist. Okay, so what was our solution? Well, we say let's take a fixed degree truncation, a fixed order truncation of the Taylor series for e to the minus I little hi theta. In other words, the final way we're scrambling the circuit is by taking ci times hi times the kth order Taylor series truncation of e to the minus I little hi theta. Now, one thing is good about this, right? At least each gate entry now is a polynomial in theta because the Taylor series is a polynomial in theta, and then by the path integral, right? So is the output probability. So that's good. We actually have a real polynomial here, and we can do exactly the same thing. We can extrapolate. We can recover this polynomial in the single variable theta and evaluate at 1 to get back the output probability of our worst case circuit. That works. But it has a big caveat, which which we lost a lot of sleep over way back in the day when we first thought about these arguments, which is sort of the elephant in the room, which is these truncations, they give us the polynomial structure, but they also make the distribution over circuits supported on circuits that are not even really circuits. They're slightly non-unitary. They're not unitary because we threw away some of the Taylor series of a unitary matrix. And one might worry that when we do this, the hardness that we're getting at the end of the day is coming from this non-unitarity, not from the random circuit, okay? Well, I go through this quickly these days, but in fact, proving the following statement was like 2/3 of the paper. Just that we're able to prove that in fact that's not the case, that the complexity of computing the truncated circuit output probability is exactly as hard as the complexity of computing the non-truncated circuit, the unitary circuit. And that took a lot of work, but intuitively it's really clear why, because at the end of the day we're interested in approximations to the output probabilities of these circuits, right? Like to the n additive error approximations. And the Taylor series truncation, the error that we're getting there is so much smaller than 2 to the minus n. So we can use that in like a 12-page proof to show this. Luckily, though, this is all for historical value, since after us, Ramis Movasag showed a very similar argument, but changing one thing. So again, it's very similar to Lipton, but he changed the way the path from the worst case to the random circuit, and he changed the path in a really clever way so that that path stayed unitary throughout the path, whereas our path sort of starts and kind of ever so slightly deviates from unitary. The rest of the argument is exactly the same. So it's a Lipton-style polynomial extrapolation argument and so on, but he changed the path, and it's a very nice result. Nonetheless, I want to be clear, it's just about the analysis. Right? We were also able to prove this hardness was robust to approximation, just like Ramis was. It's just his method does it in like 2 pages, where our method used 12 pages of really ugly stuff. Okay? Yeah.
So the extrapolation to non-small theta, namely theta equals fixed truncation, makes me really uncomfortable.
Yes. And I think I'll formalize that discomfort in a moment. Yeah. But let me try to do that. Okay, so this is why. So okay, I want to talk about sort of the frontier here, which we've been working on for years, which is improving the robustness of these arguments to additive error, which I'll call imprecision, okay? So far we've assumed that we can compute most of the we can compute these output probabilities of most of these random but correlated circuits exactly, with no error whatsoever, okay? But that's not the actual situation, as I said before. The actual setting is approximate. In other words, you should think of it as there's this ideal polynomial in a single variable theta of degree m, and our goal is to estimate p of 1. That's the same goal as we had before, okay? But we're given faulty evaluation points because we have access to this faulty algorithm. And what the faulty evaluation points are, they're like theta I, yi, and so on. We're given many of them, like a polynomial number. And we're promised that for most of these points, the yi is delta close to p of theta I. For some delta, let's think of that as like 1 over 2 to the n or something like that. Okay, so most of these points are close to the polynomial, but some of them are wildly off. And we don't know which is which, right? Or graphically, it looks something like this. We have this polynomial in a single variable theta, that's p of theta, but we're not lucky enough to be given p of theta. We don't have the coefficients of that polynomial or something like that. Instead, we're just given these silly red points with the guarantee that 2/3 of them hug the curve, are within delta of the curve, and 1/3 of them could be wildly off. But we don't know which is which. Okay? And from that, we want to get an estimate to p of 1. That's the goal. All right, so this is very much an error correction sort of problem. In fact, all of our work on this comes from the state of the art in error correction. I'm going to spare you the details because I want to talk about noise. But let me tell you the state of the art, which is that there's an algorithm. It's actually not efficient, which is interesting, but we don't care about that for the same reason we don't care that Stockmeyer is not actually an efficient algorithm. It uses an NP oracle. And what the algorithm does, it's a classical algorithm, it uses these faulty points to output some polynomial q with the property that q of 1 minus p of 1 is less than or equal to delta, that's the closeness of each of these good points, times an exponential blowup, which is 2 to the m log m. Okay? Now sorry?
So the reason you don't care about the oracle is that you know the worst case point is far harder than NP.
Precisely. And I didn't really get into that, but yes, that's the whole point. It's sharp p hard, and sharp p hard even with an NP oracle we think is a still hard problem. Yeah, yep. Okay, so the point is though, when we go all the way out to 1 with our algorithm, we're punished for it. And we're punished by quite a bit, by this 2 to the m log m factor. M is the degree of the polynomial. In the circuit language, that's the size of the circuit, which we're thinking of as n times the depth. So n times d, it's the size, the number of gates, okay? This is the state of the art. What it means is that to cancel, or to sort of correspondingly, cancel out this exponential blowup, we need to take the delta parameter to be, correspondingly small, like 2 to the minus m log m. This is the state of the art. It's taken us several years. Every few years we make progress on this, but we're still not where we want to be. What we want is 2 to the minus n, not 2 to the minus m. Okay?
Is there
that,
to these Unenbluth type inequalities?
Sorry, to the?
Unenbluth type inequalities.
Good. That I don't know, actually. I'd be happy to talk with.
There's a little.
Oh, really?
So you have some degree on control on the degree of the polynomial. It might be that you have to use higher order polynomials.
Okay, I might not mind that, depending on what the situation is. Maybe we could talk about that, actually. Okay, but what I want to talk about, how much time do I have, Norbert?
Another 15 minutes.
Okay, perfect.
If there's lots of questions.
Okay,
Last if you want.
perfect, because I would love to talk about noise. So far, I was very careful to say that I wasn't considering noise. But uncorrected noise is the defining characteristic of the NISQ era, right? I think when we start to be dealing with this noise in a reasonable way and correcting it, I think we're already sort of heading out of the NISQ era, essentially by definition. And so we're really interested in this question: is there a sense in which this quantum signal survives the uncorrected noise? Okay. And it's particularly important because noise is absolutely overwhelming in near-term experiments, right? We can look no further than Google's first RCS experiment, which they estimated that their signal, their 53-qubit fidelity, was 0.2%, 99.8% noise, and every indication that if they had made their system size larger without further decreasing their noise, their signal would be decreasing exponentially. Okay? So in what sense can we say this is hard? Well, the first thing we need to ask is, how do we theoretically model this noise? And that itself is not obvious. Right? It's not obvious because we don't really understand the full 53-qubit noise channel of the system. Even doing that is well beyond our capabilities. But the first model that every theorist loves, I think, right, is single-qubit depolarizing noise. So the first thing we're going to think about is each layer of random gates is followed by a layer of single-qubit depolarizing channel, which is this guy here. It's essentially like we're sprinkling random polys at every point in our circuit, okay? Or, in the circuit diagram, we're looking at something like this. These rectangles are our gates, our random 2-qubit gates, then that's the noiseless circuit. The blue dots are the single-qubit depolarizing channel, right, which are like random polys. Okay, and I think I already got this question, but in this discussion, at least in the beginning, I'm always going to think of the noise strength as constant. Okay, so this gamma is going to be a constant as the system size grows. Okay, we can think about other regimes, but this is the sort of most natural asymptotic regime to be thinking about, because again, we're thinking about n is really big. Okay, I want to be really clear. This is a popular model. A lot of theorists talk about this, but we know there's more going on here. Okay, so it's oversimplified, and we're going to talk about how dangerous making these simplifications are in a moment. But for the current for the next few slides, let's think about depolarizing noise. Now, it's actually really easy to understand at intuitive level what's going on with depolarizing noise, right? Why is that? Well, what are you really doing? Well, depolarizing noise intuitively is taking your state, and it's making you closer and closer to the maximally mixed state, right? So it's adding entropy to your system. Now, if you keep going, you have a layer of random 2-qubit gates, and then you add a little bit of entropy to your system, and then you have another layer of random 2-qubit gates, and then you add a little bit more entropy to your system. You never release this entropy in any way. You never measure or add a ancilla qubit or something like that, which is what saves us an error correction, of course. Right? Then it's very clear what happens. Right? What happens? You converge to the maximally mixed, or the uniform distribution. That is clear. It's absolutely clear. Okay? So, what's very clear is at some point, if we keep evolving our system, we're going to reach the maximally mixed state. Right? What's less clear is how close are we for a given depth to the maximally mixed state. Right? That's not clear. It's clear that you eventually get there because you're just adding your entropy, but it's not entirely clear how quickly that entropy is accumulating, how quickly do you reach the maximally mixed state. And in fact, in the early discussions of the quantum supremacy experiment, 53-qubit experiment, they thought that the answer to this was 2 to the minus d times n, if d is the circuit depth and n is the qubits. If that was the case, so in other words, if as you increase your depth, you get closer, that's reasonable. But also, as you increase your system size and keep your depth fixed, you still get exponentially close to the maximally mixed state. If this was the case, right, this would be really, really bad news for the near-term era, because in the near-term era, the game we love to play is that we love to say, okay, if the depth is fixed and reasonably small, then you can take the system size to be as large as you want, and we're not decohering too much worse. Right? We're not getting much, much worse, much closer to the uniform distribution. No, they were saying 2 to the minus d times n. It turns out that's not correct. We were able to, so we now know that the answer is 2, at least for Haar random gates. It could be different for other gate sets. It's kind of an open question. But for Haar random gates, we now know the answer is 2 to the minus theta of d, close in total variation distance. So this is both an upper bound and a lower bound. The upper bound has been known for a long time, since the prehistory of quantum computing. You might expect that people like Dorita Haranov were thinking about this in the context of the fault tolerance theorem. Right? They were saying, how badly does noise kill you? Right? And they showed an upper bound, and that's an upper bound for any circuit, not just a random circuit, of 2 to the minus d. Okay? We showed a lower bound for most random circuits. So we showed that, in fact, this is the answer. You're 2 to the minus some constant times d, close in total variation distance. In particular, it rules out this scaling of n in the exponent, which would have been catastrophic for the near-term era. Okay, but I want to say that already this 2 to the minus d is not so great. Okay, it already rules out any sort of scalable quantum advantage with depolarizing noise, at super logarithmic depth. Why is that? Because if d is larger than log, then 2 to the minus d is smaller than any inverse polynomial quantity. Well, what's wrong with that? Here's what's wrong with that. Uniform distribution is easy to sample from, essentially by definition. Okay? Now, the TVD, the total variation distance, or statistical distance, the closeness between these two distributions, it can be used as a lower bound for the number of samples you need to take to even distinguish these two distributions. It's like 1 over the TVD, right? And so if your TVD is smaller than any inverse polynomial quantity, then 1 over that TVD is going to be super polynomial just to distinguish your output from the uniform distribution. That's really bad news. Right? So what this means is that we've known, and we've known since the 90s, if we're considering depolarizing noise alone, we can't take our depth to be larger than log. That's not going to work. Okay? So what about noisy shallow depth circuits, right? So, in particular, by the same result, if the depth is at most logarithmic, then, in fact, the output distribution of the noisy circuit is inverse poly far from uniform. It's also inverse poly close to uniform, but the point is here that it's inverse poly far from uniform, okay? Which at least gives us hope that the whole business is not worthless at log or shallower than log, yeah? Because we haven't decayed so much that we're so close to the uniform distribution at that point. Okay, but this is exactly the setting of a paper that came out about a year ago, which I think is a really nice paper, which gave a classical algorithm for sampling from the output distribution of noisy log-n depth random quantum circuits. Okay, and I'm being very careful about this. I want to be, because it's all of these adjectives are extremely important. Noisy means depolarizing noise. Okay, not something else. Depolarizing noise. And exactly log and log depth. You can have a constant times log, but you can't be smaller than log. And if you're any larger than log, you may as well sample from the uniform distribution. It will do better than this algorithm. Okay? But nonetheless, there was this important question about log depth, and they said that, in fact, this is an easy problem classically. I want to tell you a little bit about this, because the idea is simple. The analysis is very clever. The idea, though, is quite simple. It's to write the noisy output probabilities as a path integral again. Okay, but now it's going to be a path integral in a different basis rather than the standard basis, which is what we saw last time. We're going to write each of the noisy output probabilities. I'm denoting those as p twiddle of x. X is any outcome you like. Okay, n-bit string of c. That's this giant sum, just like before. Now the sum is not over an exponential number of computational basis strings, but rather over all possible d+1 tuples of n-qubit poly operators. Okay? But for us, it's not that important. The important thing is, again, this is just like before. This is an exponential size sum. It seems like you should panic because there's so many terms in that sum. But in fact, if you look at each term, it's quite manageable. It's some sort of efficiently computable function, f, which is a function of the circuit and the path and the input, x. I won't go into this in a huge detail what this is. It ends up being the product of a small number of poly transition amplitudes. If you know what that is, that's great. If you don't, not that important. The point is that you can compute that efficiently. And then the really important thing is, because of the characteristic of the noise, the depolarizing noise, very special to depolarizing noise, we have a contribution which is something like 1 minus gamma, that's the noise rate, we thought of that as a constant, to the Hamming weight of that path. Right? This Hamming weight notation, I mean, by definition, it's the number of non-identity operators in the path S. Okay? So now, their observation, which I think is really nice, is that, there's the key point is that the output probabilities of the noisy circuits in this poly basis are exponentially suppressed in the weight of the path. So here's one really bad way of computing this output probability. Just compute term by term. That doesn't make much sense, because if we're okay with approximations, which generally we are, right? The point is that, if this Hamming weight of the path, the number of non-identity operators, is really large, we shouldn't really be caring about that term, because it's exponentially suppressed. That's the idea. Now, so what's the classical algorithm? It's exactly what you would think. You just sort of compute this term by term, but you only compute certain terms. So in other words, you're throwing away some terms for which the you know, the poly weight of that path is too high. Okay, that is the algorithm. It's very simple to state. The analysis, though, is interesting, and this is where we start to come in. We've been thinking about this for a while. Well, how do you bound the truncation error? So or maybe truncation is the wrong word, but you know, you're losing a lot of your path in you're losing a lot of your terms in the polypath integral. So how did sorry? Yeah, truncation is it's overused. But anyway, so what I want to say is that the way they bound the error relies on a special property called anti-concentration. Anti-concentration is a property of the output distribution of a random quantum circuit. And one thing we know about it, this is what anti-concentration means, is that the output distribution of a random circuit is sort of well spread. It's not uniform, but it's kind of uniform-ish. Okay? You can look at this offline, what exactly this means, but what I want to say is that anti-concentration essentially trivially means that, it's a good name, it means that the distribution is not too well concentrated in a small subset of the outcomes. It's sort of, you know, relatively well spread. And this property we know, happens when you have a sufficiently deep random circuit. You start to anti-concentrate. That makes sense, right? If you have a deep random circuit, eventually you start to to be sort of well spread over all of your outcomes, right? If you don't have a deep enough circuit, you're probably somewhat peaked. Okay, and so at what depth does anti-concentration happen? Well, it turns out we understand this, and we understand this in particular from some research that I was a part of. It starts at log depth, okay? So this is why this algorithm of Aharonov and co-authors requires at least log n depth, because their analysis, the way they're bounding the loss when they truncate the polypath integral, uses this anti-concentration property. This anti-concentration property starts at log depth, and it fails catastrophically before log depth. Okay? So, in fact, if the circuit is too shallow, their algorithm does not work. If the circuit is too deep, their algorithm works, but there would be no reason for the algorithm because the uniform distribution does better. So they're really at this knife's edge. But let me tell you my interest. And I've now been thinking about this for about a year, which kind of mixed success. Okay. I need maybe two more minutes, something like that. Let me tell you my interest. My interest is in adapting this result to other noise, and the reason is because depolarizing noise is a good sort of first guess at how the noise in the system works, but no one thinks that's the actual answer, right? It's an oversimplification, a mathematical oversimplification. It's very convenient mathematically. It's not actually what's going on physically. Now, it would be totally fine if you could then adapt their algorithm to any other noise, which is, I think, their sort of argument. Their argument is like, well, maybe our algorithm is not that specific to the actual noise choice, and then that, of course, would be great or terrible, depending on what your perspective is. But I want to know if that's actually the case. So if I change the noise to be more physical, does this algorithm stop working? That's the motivating question. Okay. So let me tell you what we've noticed. We think we've studied this a lot for many different noise models, and we think there's a divide between something called unital noise and non-unital noise. Okay? So what does it mean? Well, mathematically, unital is very simple. It means the identity maps to the identity, right? And for every unital noise model we've looked at so far, it seems like this algorithm is working quite well. I'm not going to bore you with what exactly the noise models are, but it seems like when we have unital noise alone, depolarizing is a good example of that, by the way. But then it works. But the really interesting question, I think, is what happens if you have a more realistic noise model, which would in general involve both unital noise and non-unital noise. Here we have, I think, of what I thought was a really surprising result. So let me tell you what the answer is, what we came up with, which is that it turns out if you have a different noise model that's, I think, more realistic, it's still oversimplified. It's not the final answer, but it's more realistic than just depolarizing noise. If you have some constant rate of a unital channel, and then a constant rate of a non-unital channel after each layer of gate, and then you have another layer of random gates, and then you have, again, unital channel, non-unital channel, etc. In fact, what we showed is that no matter the rates of these two noise channels, as long as they're both constant, it doesn't matter if one is smaller than the other, doesn't matter at all, as long as they're two constant, you don't anti-concentrate at any depth. You never anti-concentrate. In other words, this distribution never becomes flat enough to use the analysis of this Aharonov algorithm. Okay? So this is where I love to end, at least in terms of my contributions here, because what that means is that we don't know the easiness in these cases. But also, it turns out the anti-concentration is used in the hardness argument, so which I didn't really talk about. But we don't know hardness there either. So we know nothing about these more general noise models. It's a very interesting question because this is a more reasonable noise model than just depolarizing alone. Let me stop. I know I'm running out of time. Let me stop. I'll ask a few open questions. So first, can we prove the hardness of sampling from random circuits in the noise list case? We didn't finish that. That involves improving the robustness and precision of these arguments. How hard are random circuits with the low noise regime? What if the noise can depend inversely on the system size, right? It's not clear how physical this is, but there are many interesting reasons, generally having to do with benchmarking, for caring about this model. So I think it is well motivated, even if it's not totally physical in the asymptotic regime. Then finally, have current experiments achieved the right Goldilocks regime? This is an orthogonal question to all the questions we were asking, which are all asymptotic scaling arguments. Let me tell you what I know about that very quickly. For boson sampling, that's this linear optical demonstration that's been done by USTC and by Xanadu. I think the answer is no. We're able to come up with a tensor network algorithm from my group in the last year that actually simulated their systems. And it simulated their systems fundamentally taking advantage of the predominant noise channel in their system, which is photon loss. What we think happened is when they said how hard, they estimated how hard their system would be. You know, they said, I don't know, 100,000 years, whatever it was. So that's an estimate. They were not taking advantage of the noise. It turns out there are algorithms that can take advantage of the fact that their photon loss was very high to simulate that much quicker. We can currently simulate their largest scale system in under an hour with a modest number of computational resources, okay? For random circuit sampling, actually we don't know. That's it, okay? That's all I want to say.